Hello, everybody. Thank you for joining this session. So my name is Mahantesh Halappanavar, and as you can see, we have a fairly big team here, and much of this work was done by Moqsadur Rahman from UTAP, and we also have several other members, and Joe Aguayo is also here attending the talk. Um, and one of my communication teachers basically said that we should begin our presentations with a story. So I'm going to start with a story. So one evening, an old Cherokee Indian basically tells his grandson that there is a great battle among us between the two wolves. So one wolf represents all that is good in us, and the other wolf basically represents all that is bad in us. It's like anger, jealousy, hatred, and so on. And the grandchild thinks for a little bit and asks which wolf wins. So then the grandfather basically says, the wolf that we feed. We see cybersecurity as this ongoing war between that is good and that is bad, the attackers and the defenders. And we can only win by feeding good information. Say, for example, the log4j, the log4shell flaw was identified, and within the first 3 hours or the first 2 hours, there were about 40,000 attacks that were made. And within just the first 3 days, there were close to 1 million attacks that were made. So it becomes extremely important that we want to reduce the time between vulnerabilities discovered and by the time we want to mitigate and fix this flaw. Right? So our goal is to build tools, efficient tools that can minimize this action so that we can take efficient actions very quickly. But then one might wonder, why are we even having and introducing these vulnerabilities, right? So like, as Edgar Dijkstra observed, if debugging is the process of removing bugs, then programming must be putting them in the first place, right? So nobody wants to put them intentionally, but it happens that it's a very difficult and complicated process. And in the process of developing a software or hardware, bugs do get introduced. But a bug only sort of becomes a vulnerability eventually. And in this slide deck, we'll see what kind of input data we can look at, a different variety of data, and how what kind of methodology we can develop to make it into a knowledge graph. And then we will see the power of using a knowledge graph and being able to query information with a few case studies. And a bug only becomes a vulnerability if it can be exploited. Right? So we do have bugs, several bugs, but if a bug cannot be exploited, it does not become a vulnerability. And when it is exploited, an attacker can use this exploit and make the hardware or the software behave in a way that it was not originally intended to. We can say that this system has been compromised at this point. So MITRE introduced this systematic common language of explaining what a vulnerability is and how it can be efficiently distributed across the world more than 2.5 decades ago. And at this point, there are close to 300,000 or a little over 300,000 different vulnerabilities that have been registered. And there are close to 500 different numbering authorities that exist worldwide, that continuously feed in different vulnerabilities. As an example, one vulnerability that was disclosed in 2004 was the SQL injection vulnerability. And as you can see, these vulnerabilities exist in very specific products. For example, this existed in the post-GRE SQL library 0.5.2, where the attackers could execute any arbitrary SQL statements, right? So the idea was not to enable arbitrary SQL statements, but now an attacker can compromise this system and be able to run anything that was not originally intended. So that's the first data set that we have. And as you can see, there is an increasing number of CVs that get disclosed every year. It's in 2024, there were about 40,000 different vulnerabilities that were disclosed. So they do come to us at a rapid pace, and we are not always able to understand and mitigate and build patches very efficiently for them. So how do defenders make sense of all of this? Right, so for that, MITRE also helped develop this second class of structured information called as the common weakness enumeration. So here, common basically gives us a common language where people talking about it can come to a common understanding of what it all means. And the CWE, it's a hierarchical organization of information. And the deeper down we go in the hierarchy, we get more information. So it provides us a blueprint on how we can understand these different vulnerabilities, software flaws, how can we think about them, how can we go about mitigating them, and how we can even prevent them from happening. It's while CVs were very specific to a product, weaknesses are somewhat abstract. They are applicable to a broad set of different vulnerabilities. And we have about 1,000 different weaknesses, while we had more than 300,000 different vulnerabilities. So we have about 1,000 different weaknesses. So while one was very product specific, the other one, the weaknesses, is more abstract in its construction. And then we come to our first task. So given a vulnerability, can we automatically map it to a set of different weaknesses? Right. So vulnerability can now be defined in terms of weaknesses. So why we want to define it as a weakness? That's because we have a lot more abstract information that's available to us. So we want to take a vulnerability in a specific product or a protocol or a hardware tool and map it to a set of different weaknesses. And here, the deeper down we go in the hierarchy, the more information we can get about a given vulnerability. So that is our first task. And while this was done manually by MITRE engineers in the beginning, so only about 1 to 2% of information has been mapped manually by humans. Right? So it's not really a scalable and scalable approach doing it by humans. So we want to automate this process. That's our task one. But we also have a fundamental challenge in why this is a difficult task for doing it automatically using machine learning approaches. Good machine learning approaches, especially supervised learning techniques, need availability of data, right? We need good training data set. But as we can see in this distribution, a large number of these manually classified or manually mapped information exists for a very small set of CWE classes, only about 12. While a vast number of them, so we said there are about 1,000 different classes or different weaknesses, a large number of them don't really have much information to be trained. And in fact, it also turns out that when we split them across time, we can see that a lot of information exists for something that happened before, that exists before 2017. And so for anything that comes after 2018, there is not much information to be gained. So it becomes a difficult problem on its own. So we discussed all of this from the defender side, right? So this is what we can observe in our network. This is in our products. So this is what we can see. But now let's take a look at what happens on the attacker side. So from the attacker side, there is a definition. Again, MITRE helped develop these common attack patterns, which basically says, given a weakness, how can attackers go about attacking them? And so again, the idea is that also it will enable and train even the defender as well. So in order for for somebody to exploit a given vulnerability, they can come up with very specific mechanisms or attack patterns. And this is an enumeration of all those different attack patterns that are currently known by human beings at this point of time. That's currently known. So we know about 600 different attack patterns. So they are very specific information. And again, the CAPEC link us back to weaknesses, not a very specific product. And they give us this general pattern of how to build these attacks, right? So which can then be employed by different adversaries. And they are also very specific to applications, right? They exist in like SQL or in very specific products. So that's one of the key ideas here. And there is also a hierarchical structure to attack mechanisms, right? So for example, one could engage in different deceptive interactions. Within that, there could be spoofing, identity spoofing, content spoofing. Within identity spoofing, there could be like you want to fake the source of data. And so there is a hierarchical structure. The deeper down you go, you get a lot more context, right? So you can get context from all the classes that are above that particular thing. And common examples could be like HTTP response splitting, SQL injection, buffer overflows, like very popular clickjacking, like initial interaction. So our task two then becomes, given we already mapped a given vulnerability or to a weakness. So now what task now becomes like, can we map weaknesses to CAPECs, right? So like attack patterns, how can they be exploited? So now we slowly start getting closer to what the attackers are thinking about and how they can come and compromise our systems. So we take a given CVE, map it to CW, and we take a CW and map it to CAPEC. And the original problem of lack of data for training got exacerbated at this point, right? So there is even less information for us to train automated techniques. And when we think of these specific CAPEX and expand them into an application, into a full network context, right? So CAPEX was very specific to one application, but if we think of this very broadly, so there is another set of data that was again organized by Matter. They call it the Adversarial Tactics, Techniques, and Common Knowledge, or ATT&CK, which basically gives us the entire mechanism of how advanced persistent threats happen over a period of time. And they have very detailed tactics, techniques, and procedures. So tactics are different stages. They are organized along columns. And techniques are very specific to a given set of tactic. For example, one tactic could be initial access. How do you gain initial access into a network? Or how do you do lateral transition when you are inside already? And then finally, how do you take or get the benefit out of this whole attack, right? So you can either exfiltrate the data, or you can compromise the system, or you can just spoil an web page and so on. So there are different stages, and then there are exact procedures, and the attack itself at different levels, it calls for CAPEX. And CAPEX will call for the weaknesses, and weaknesses will have very specific vulnerabilities that are connected to them. So in summary, we have CVEs, CWEs, CAPEX, and attacks. And there are different sources of data that all that come to us all in different formats and varieties and so on. And there are also these very specific metrics and numerical values that are attached to each vulnerability, basically specifying how important a given vulnerability is, and so on. And CISA also publishes this known vulnerabilities in the wild, so which ones are being exploited at this point of time. And MITRE also releases these top 25 CWs, like every year and a half, they release these top 25, which were the ones that got exploited the most. So we have plenty of information coming to us. And now the idea was to systematically process all of them and then build a knowledge graph. But before that, we need to see how are we going to accurately map between these different blocks of information. Right, so the first task becomes, how do we map a given CVE, a vulnerability, to its weakness? So we developed this Siamese model that basically feeds in CVE on one side and CW on one side, and uses encoder models such as BERT to build a vector representation of the CVE and CW, and it asks a binary question. It's like, okay, is this CVE best mapped to a given CWE, right? So we pose this as a link prediction, but overall you can think of this as a multi-class hierarchical classification problem. It's a given CVE can go into any one of these different CWE classes. At the top level, we have about 34 or so. So which one is the closest one? So we basically take this link prediction, and sometimes because of this link prediction, that sort of becomes the learning parameter here. We want to come back and back propagate and see how to build these encoders correctly. And because sometimes they have also been pre-trained or cyber specific information or something, we also want to make sure that there is no loss of information. So we also add the reconstruction decoder. So we published this work in 2021, and it also received a Best Paper award back then. And as we observed in our preliminary benchmarks, so B2W-BERT was one of the best in the class for predicting or accurately mapping a given CVE to a CWE. So now we not only have information at the highest level, which is usually also provided in the National Vulnerability Database, but we also have a lot more specific information. And as we can observe that when there is a lot of information, like for these specific classes of CVEs that came earlier, there is plenty of information, and any given method can do really well. It can get to close to, a couple of them were the state of the art in 2021. But as we can see that our approach really shines when there is lack of training data. These are like the zero shot or the few shot learning approaches. So we observed that we do really well with the first for the first set of the mapping problem. So for the task 2, where we had to do CWE to CAPEC, we realized that the amount of information that was available to us for training was even less, right? So the first approach we tried was to do link prediction. Again, we use the same approach, do it as a binary problem, and then we can come back and train. But we also took advantage of the new advances in the large language models, and using sequence to sequence model like Google's T5, for example, we could now do prompting. Like we can ask, give me one weakness to an attack mapping, and T5 after some pre-training was doing really well. So it would say that CWE20 is linked with this CAPEC 10. But we could also ask a slightly different question for the same CWE, give us two weaknesses. Let's say it would give it. Or it can also express and ask these questions about the hierarchy and so on. And as we observed that both models were doing fairly closely well. But of course, we did not really have a lot of information to basically train these models. That's something, it's an ongoing work. So now we have everything mapped together, but just asking an LLM is not going to be sufficient. And as you can see here, and if we just ask, so this was asked to a Llama 3 model, and we can ask, find the CAPEX related to this given CV. Sometimes Llama can come back and say that there are no currently mapped things. But once we ask a RAG-based system, it can basically come back and give us a lot more specific information. And so what it tells us is that even the state-of-the-art large language models sometimes can be very inefficient in giving us the accurate response because they don't necessarily have all the context. Then we ask the question, can we build this knowledge graph efficiently well? So that was our first task. So we built this automated pipeline where we can extract some information on a daily basis, like the CVEs that come at a rapid pace, and the CWEs and CAPEX that can also have fairly frequent updates. And then there is some information that comes at a slightly slower rate. So we run it at a slightly smaller rate, like on a weekly basis. And then we extract all the information, store it, and then update and load it into a Neo4j graph database. So overall, our scheme looks like this. And we have several different node types. We basically talked about CVE, attack pattern, CWE, but the attack pattern also has quite a bit of information like malware, what is the course of action, mitigative actions, intrusion, what threat group are we talking, and so on. So we basically collect all of them, and we also establish the relationships now. So like linking between CVE and CWE, linking between CWE to CAPEC, which we are using with very sophisticated language models, but some we can extract from the data that already exists. Right? So attacks also have links back to CAPEX, and they also have links to malware and then mitigative actions and so on. So we are extracting all of this data, building the database, and now this enables us to query the information efficiently. Let's say you can go from one way, and for a given CV, you can go all the way, okay, which attack technique should I be looking at? Attack techniques are, again, very specific instantiations in the real world, while CWEs and CAPEX are sort of abstract definitions. Right? So they're talking about things in a broader sense, while vulnerabilities and attacks are very specific to products or an attacker type or an attacker group, something that has already been done in the wild. Let's say you can go from one end to the other end, or you can come back and go from the other end to, right? So for a given attack pattern, you can come back and ask the similar questions. Right? So what CVs are associated with us. So now we can go and look into a few specific case studies. And the first case study is we to just look at all these top 25 CWEs, right? So these are critically important for a lot of people in the cyber defense world. So we can ask these questions. So for all these top 25 software CWEs, give us what are the specific attack techniques that we need to be concerned about, right? So who is attacking us? For example, for this 94 CWE and 94 improper control of generation of code or the code injection, we basically found this technique, HTML smuggling, is one that we should be really concerned about. So we can start asking such questions. And usually the top 25 software list will just give you this information, right? So they're not giving you a lot of other information as well. And we can also look at very specific information, say for given this attack T110, which is a brute force or password guessing kind of an attack mechanism, we can ask what malware should be should we be concerned about? So what mitigative actions do we have? What data components, or like what are the attack patterns, the CAPEX that we should be worried about? Which campaigns are actually doing this, right? So which campaigns are using it, and what are the tools that are available to us, and so on. So we can start posing this as a cipher query. We basically said, look, for this one, we want to get all of this information, and you can also limit the amount of information you want to look at, and then you sort of get the information come back to you. And a few other specific examples we looked at was one of them was the scattered spider, which is a financially motivated group, and they were and they did the very popular MGM Resorts breach in 2023, and they shut down the casino for multiple days. But if you think from the casino's perspective, it is an extremely important and revenue blocking attack. So they would have lost billions of dollars. Right, so we can ask questions about, like, given this particular group, what kinds of weaknesses are we concerned about, right? So which ones should we be aware of? Yes, so it comes back and lists several different CWEs that we can now extract from the given threat group to the CAPEX that are being used to the weaknesses that we need to be concerned. But we can also go one step beyond. So which are the vulnerabilities that we should be worried about, right? So there's a lot of information that can come back to you, but it's a very systematic way of looking at the information. And we can again do the same for another different one. For the old Typhoon, which was a state-sponsored attack that sort of infiltrates into the US critical infrastructure. That's like, what kind of attacks are we expecting on the critical infrastructure? It could be like your power distribution, your water distribution, transportation, things like that. So once the critical infrastructure is down, more or less the economy sort of starts shutting down. So that's the consequences we can look at. And again, we can ask the same things like for the Russian GRU targeting Western logistics, the existing approach without having to have the very specific knowledge graph and the ability to go across different hierarchical stages, your information extraction gets very limited. Right? So you can only extract so little information. But with the ability we provide through a knowledge graph, now we can incorporate hierarchical relationships like the CAPEC precedents, right? So child-parent relationships within the CAPEC and the weaknesses, and now we will be able to extract very specific information for a given threat group. Yes, we also observed the same for the stop ransomware attack, and basically by using two-hop hierarchical extensions across CAPEC and CWE relationships. So now the knowledge graph sort of provides us extreme ability. Now we can also hook it up with a lot of other things as well. And while this is all good, this is the information that we explicitly fed into the system, right? So, but that's always a limited amount of information. So we can also ask, given all of this structure, can we predict some of these relationships without putting them explicitly into the system, right? So the Neo4j tool also provides plenty of tools for us. For example, the Graph Data Science library also has this Adamic ADAR metric, which basically says that if you're connected to a node, which is also a rare node, right? So it does not have that many edges coming out of it. It's just like the page rank kind of idea. You are important because you are linked by other important web pages. So that sort of gives it a higher weightage. Or you can simply count how many edges already that exist between two given nodes. If there are a lot of other common neighbors, you can believe that with a high probability, there might also be an edge. So we can start using these topology-based metrics. And what we discovered using this topology-based discovery is that we were now able to link between CWE 308, which is a single-factor authentication, and CAPEC 151, which is an identity spoofing. Conceptually, we can think that weak authentication mechanisms means that, okay, anybody might be able to very easily spoof, right? So there is a good inherent connection between these two, but we did not explicitly put it, but it was discovered because it had 14 common neighbors and a very high Adamic ADAR score of 5.41. Similarly, between improper input validation and buffer overflows. It's just because the scores are quite high and they have a lot of neighbors. So the topology based becomes a very distinctive structural overlap. So it's a very powerful way, and you can also rate different relationships using these different metrics. So to quickly conclude, we demonstrated that using large language models and the ability to do hierarchical classifications. So we can find and connect a variety of different information in a very, very effective and powerful manner. And we demonstrated this not only for frequently occurring instances, but also for these rarely occurring instances, right? So something that is very hard to train for and get good accuracy results from. And we are also able to exploit quite a bit from the hierarchical relationships. And we also scaled the V2W burden onto several generations of NVIDIA systems so that we can do it very efficiently and very fast. So we have published all this work. And in the ongoing work, we are integrating it with a GraphRag framework where you can interact with this in a very smooth manner. And all the responses from the LLM will now be guided with the context that we get from the knowledge graph. And we are also integrating it with the cyber operations at PNNL. Joe is leading that effort. And we are also doing a few benchmarking efforts as well. It's like, do we really believe that this can extract all of it? So we have created a large benchmark data set with input from the cyber experts as well as, language assisted, AI assisted data set as well, all human with human validation at the end. So we plan to do that validation as well. So with that, I will end the presentation here with a few references. And we are happy to take one or two questions that you might have.